as one of the free things that you got in Frosted Flakes. They had something called Diving Tony, which basically worked under the same principle. Unfortunately, the actual Diving Tony toy had a small leak in it, and so it worked a couple times, and then it would just sink to the bottom. Eyedroppers work a little bit better. And hopefully you can see that there's an eyedropper in there. And so what I'm gonna do is I'm gonna magically, it's not quite set up for the full effect. Yeah, I'm gonna have to light knuckle it. So as I squeeze it, the eyedropper falls. And the question is, why? And I open it up for the group to dazzle. If you need to experience it yourself, I'll be glad to hand it to you. So why, when I squeeze it, does the eyedropper fall?
Can you squeeze it at the top?
Pressure.
Pardon?
The pressure in there, you're applying different kinds of pressure. So, like if you do it at the top, the eyedropper lowers. But if you do it like in the middle, it would think up. Can you do it like?
All right,
squeeze
so-
in the middle?
In the middle,
Yeah.
it also goes down.
It goes down.
At the top it went down, and then at the bottom, it also goes down.
It's the pressure.
You are correct.
Is it the displacement?
What about it? Pardon?
Is it the displacement of the pressure? It's the fact that the pressure is moving.
The pressure is moving. What do you mean by that?
Instead of staying, I don't know, I guess in equilibrium, if you're putting pressure in different spots, so it's making.
You
All
might
of
be
the-
almost onto something. I'm not quite sure.
all-
You,
It's making all of the water move, which moves the hydraulic.
ah. Okay. The way that you described it, I want to say not quite, but it's also possible that the way you're thinking about it, just the words didn't quite match. You are right. So there's something in there.
Yeah,
Is it because when you squeeze, you're changing the area of the water, I guess, or liquid, and it's causing the pressure to change? Or maybe because you're applying a force on it?
All right, I am applying a force, therefore I'm applying pressure.
Yeah, which causes it to move.
Can I try?
Oh, good.
Imagine it just explodes.
what kind of water is in
Is it
Like tap water.
Wrong kind of water.
What's that?
it? What could be,
What about the air in the
sparkling
dropper?
water?
Cause when you press it, it changes the pressure of the air. The air, it affects, it's going up and down. Oh.
What, the air's going up and down? The air in the dropper, is that what you're saying?
Yeah, if the pressure goes up, the air starts sinking. I don't know.
If you look at the dropper, when you squeeze it, what happens to the water in the dropper?
It goes out.
Where'd you
Oh,
go with it?
It goes in and when she releases, it comes out the water.
Yeah. So as you squeeze it, as you apply pressure, the air actually shrinks in space. Which does bring up an important principle here. There are a couple of different principles. Gases compress easily. In other words, I can squeeze gas into a smaller space without much trouble. But why does the gas shrink in space? How do I increase the density of the gas there?
Changing it to a liquid?
Pardon?
Changing it to a liquid?
Ooh, no. That'd be cool if I could do that, but no, that
That'd be bigger.
would require much more pressure.
Can you repeat the question again?
The question is, so when the bottle is squeezed, you can see that the water in the eyedropper goes up, therefore the air has less space. And the question is, why does the air have less, I guess, in essence, why does the water move up into the dropper?
Is it because it has less density in the water?
All right, I need to do one at a time here. I think Gabby was going first and then Caroline.
Is it because it has less density in the water, so when the pressure pushes the water, it's able to compress easier?
Less density in, oh, you said less density than the water? That is part of it, but there's some basic principles that I want to hit on here. Caroline, what'd you say?
It's cause the air, that little bark part on the dropper has air in it.
Yeah.
So every time you push air in it, will pressure on the air. Goes up and down.
Right, but why does the water go up? Basically, we had a battle of water inside the dropper and air inside the dropper, and when I squeeze it, the water seems to win. And when I let go,
Like if you just had the airdrop, or not the airdrop, the eyedropper. Like, does the liquid won't compress as easily as the gas?
it does not. So there's another thing. Ashlyn, you were saying?
I can't describe it the way I want to. But like when you just, like if you just have the eyedropper, like just by, you're just holding it, and you're trying to pick up a liquid. Like when you release it, that's when the liquid picks up. So it's like we're doing it there. Like it's picking up liquid inside. Like it's like we're squeezing the top.
All right, so you're hitting the ballpark there, but the difference is that if I've got the eyedropper in the air and I'm gonna suck up liquids, I squeeze the top, put it in the water, release it, and I create a low pressure area in the bulb. And then water gets sucked up towards the low pressure. But here, water's not being sucked up into low pressure in the same way. There is a pressure difference. But let's hit on the other comment that was made, I think Caroline made. Liquids do not compress easily. And generally, it's close enough to incompressible. I hesitate to say it's incompressible just because it is possible, but it is not easy. Like if you dive from a high enough height into water, it's like you're landing on a solid. So they say. I really don't know who's tested that one. All right, so why does the water go up into the dropper?
Because the gas is compressing, so it's allowing room for the water to go up into the dropper.
All right, so as Ashlyn is squeezing it, water moves up into the dropper. But she's not touching the dropper. Does she have Jedi powers?
Yes, no.
Ooh, I didn't realize that. Hopefully you don't have to kill us all, now that we know.
No,
Oh, you're saying she doesn't have Jedi powers.
I'm sorry, she doesn't.
And,
Prove it.
so why is it that squeezing on the side forces liquid in the middle?
Because you're decreasing the area the water has to like spread out.
Okay, I think that also covers it, but I'm gonna cut to a slightly different wording of it, is that when you apply pressure to a closed container, the pressure is distributed throughout. So whatever pressure she is applying onto the sides, that pressure gets added to. You know, it automatically comes with some pressure. She is adding to the pressure throughout the entire thing, which is why squeezing at the top, middle, or the bottom all produces the same results, because that pressure that you exert gets distributed throughout the entire water. This is known as Pascal's principle. So, external pressure shorten it to P, on a closed container. Is distributed throughout the container.
Is it distributed evenly or just?
Distributed evenly, it's added to it. So if she applies 10 pascals of pressure, then every place inside that container has an additional 10 pascals of pressure.
So it is even.
Yeah,
I wonder why they don't put it evenly.
evenly, is basically even.
Because,
Distributed makes it sound like you take wherever it's going and divide it into tiny little bits, but you're really adding it.
yeah, but I'm thinking when you distribute it, if it's not done evenly, like this part could have more pressure than this part.
No,
And
it is the same at the top and the bottom. That, what you're, in addition, the same is added to every place inside. So when you are underwater, you are feeling the pressure of the water around you, but there's also the pressure from the air above the water, which is also part of it, because that air pressure is pushing on the water, it gets distributed. All right, so we sort of come around to why water goes up into it, the air compresses, the water doesn't compress much, so the pressure is distributed. So you've got the gas, which exerts a lower pressure than the water does, it squeezes up, and the water will go up until the air pressure, or the pressure of whatever the gas is, which is air in this case, the air pressure matches the pressure from the water. Why does the stopper sink?
because it's heavier.
Yeah, well, you know, let's be careful about the wording on this, because I would contend that ocean liners are even heavier and they don't sink.
Because it's filled with water, so it's like the same weight, or no, not weight.
What is the magic word?
Density?
That's it. Chase?
Density.
Yeah. It's going to stay afloat as long as the density of the stopper is small enough, as long as it's less than that of water. And as you squeeze it or more water into it, eventually the density of the stopper and the stuff inside it is greater. Now, I have air which is less dense than water, and there's water which is the same density as water. How could I ever get a density greater than water?
Solids?
Pardon?
Solids?
No, I mean, in this situation right here,
Oil? Or like oil? Like,
let me reword the question. I think
yeah.
the misunderstanding is there, how I've worded it. In this situation where I've got the stopper there, I've got gas and water inside the stopper. As Ashland squeezes on it, I get more water, same amount of gas. But why does it fall? And at some point, I can't add water to water. That wording is bad. Backtrack. If I take, I can get away with this. If I take this and put water in it, it's gonna feel a lot heavier. If I put it into water, will it sink or float?
Sink.
Well, one of you is correct.
It'll sink because it has the same density as water.
Pardon?
Because of the density, it'll sink.
Well, so adding water, all the best I can do is get a density up to that of water. What's the difference that would cause it to sink or float? If I put water in here,
If it had more density than water,
what has more density?
that has more density than water.
This
That
container?
When it sinks,
If it does, and that's the key. If I just put it in like this, it'll float. If I fill it with water, it comes down to, is this plastic denser than water or not? You can do this experiment with they have plastic droppers now. and you can put the plastic in there and you can do the exact same thing, squeeze it, that plastic is not gonna sink. Because the plastic is not denser than water, and so the best I've done is I've gotten the density of the dropper with water in it close to that of water, but still not less than.
More.
Still not more than, thank you. If in doubt, read my mind.
I'm just trying to
No,
follow.
you're right. So why does this one sink then?
Because the density is more
What is the material?
glass.
Yeah.
So glass
The-
has a heavier density than water.
Yes. Lose all the glass I've ever dealt with. You know, is there enough material science people out there, maybe they've got glass that doesn't, but
For the most part. So if the density is the same or less, it will float.
yeah, if it's the same, then it will float unless I push it down, in which case it would, actually, it would come back up, but there is a magic density that I could get it to suspend partway in the water.
Oh,
And there's I think it's a temperature gauge with different oils of different densities and thermal expansion coefficients, so that as the temperature changes, some of the densities will change.
It makes me think of those temperature ball things.
The temperature,
It's like in a glass container and it has different liquids in it, and depending on the temperature,
we might be
the,
talking about the same thing.
the containers will either float up or sink down.
Yeah, okay, I think we are talking about the same thing.
Okay.
Ashley?
You probably said this, but what if you got a plastic eyedropper? Would it have a different effect than a glass eyedropper?
Yeah, when I've used a plastic one before, basically it's floating at the top like this, I squeeze on it and it'll do that, but it doesn't actually fall. It is incredibly unimpressive.
You need glass to make
So you need one.
It was that, I was trying to find a glass eyedropper. I think that one right there, I just ended up with my stuff as when the last time I taught middle school in Charlotte. Yeah, probably should return it someday.
I think it's too late.
Yeah, might be. There was an article written years ago, I was still in high school, and my dad had something from one of the schools where he had taught previously, and someone said, hey, there was an article written about petty thievery, and just how common it is just to, when you leave one place to go to another, that some stuff goes with you. That's my excuse.
And I'm sure some stuff stays behind too.
Yeah, so I guess it balances out. Of course, according to my wife, not enough stuff is left behind. All right, I know what you're thinking now. You're thinking the anecdotes about past life, excellent, always fun. We're doing a lot of stuff there with conceptually, but where's the math? And so, let's talk about the math. And in talking about the math, we will get into a new force.
So this force would fall under other?
No, we would add a letter.
Okay.
Instead of F-town, it's now Facebook town,
Too bad it's not Beta.
best friend town.
Yeah.
So let's figure out what that B stands for.
Buoyancy.
That's the one. So I've got something I have a liquid here. And I wanna figure out what is the pressure at this particular spot right here. So I have air up here, this is the surface of the liquid. And at some point I'm gonna call it water, but it could just be any liquid. And at some depth, which I will label as H. If you like D, go for D. If this is an equilibrium, whatever this is, if it's an equilibrium, then I know that the total force on it has to be 0. Let's see, do I want to do box on ramp or box on box? Not on. Yeah, I'm just going to do 2 of them. So I'm going to work under the assumption that any spot on that same level has the exact same pressure acting on it. Because there's no reason for the pressure here to be any different than there. I'm not throwing in, there's swirling and different temperatures and all that stuff. It's just plain water all at the same temperature. So if I look at if I think about this as in two sort of groups of water, I got my top group of water, which I will cleverly label A, and the bottom part, which I will label as B. If I look at the forces acting on them, I've got force from air acting above it. It has its weight of A. There is force coming from B acting up, a force coming from B acting down. If these were solids, we would easily call them normal forces. They're pretty much whatever the liquid equivalent of a normal force is. Then I have weight of B, and then I've got something holding it up. We'll just say it's in a container. So, why not? I just need somewhere.